Okay, this is the video for Wednesday, September 23. Still on the topic of linear transformations. This is going to be something we'll do a lot of. Let me raise the microphone sensitivity. So remember, t, which is a function from a vector space V to a vector space W, is called a linear transformation if and only if you have two conditions. First of all, for all V1 and V2 in V, t of the sum of V1 and V2 is the sum of t of V1 and t of V2. And second, for all scalars and for all vectors in V, V being the domain, t of AV equals AT of V. And I emphasize that I will use the notation that V is called the domain of T, and W is called the codomain. This word is not the one used in the book. The book, I think, uses the word target set. I am not going to use the word range because people are not sure if range means codomain or whether range means image in any case. So, and I'll maybe note 1 and 2 can be replaced with the equivalent conditions, which because they're amalgamated, I'll call them conditions 1, 2, or condition 12. Let me just say that for all A1, A2 scalars and for all 1 V2, V2 vectors in the domain, we have T of A1, V1 plus A2, V2 equals A1, T of V1 plus A2, T of V2. And so let me make some basic propositions. These are basic, but not terribly surprising. Okay, first of all, if I have T, V to W is given linear, then we also have, well, I should say for all A1 through AK, not just 2, and for all vectors V1 through VK, T of a linear combination A1 V1 plus dot 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 plus AK VK is A1 T of V1 plus dot 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 plus AK T of VK. So, and the proof of this is by induction on K. The original case is when K equals 1, and then that's the statement which is in blue is the thing above, and then from K to K plus 1, that's the inductive step, uses 1 and 2, or if you like, 1, 2. Okay, it's pretty straightforward and it shouldn't be too surprising to anyone. Okay, the second one is a little bit less obvious but totally unsurprising. T linear. Then for this linear transformation, T of the 0 vector of V is equal to the 0 vector of W. I emphasize this because we could have put this into the conditions for a linear transformation, but then we'd have to check it each time. And no, we want to use it because it's always true, but you don't want to check it every time to check something's linear. So let's give the proof. There are two proofs. here's the first proof. Since 0v plus 0v equals 0v, I'm emphasizing the difference between the 0 vector in v and the 0 vector in w, just so that you keep it straight. The input to t is always a vector in v, the output is always a vector in w. Anyhow, since the 0 vector plus the 0 vector is the 0 vector, then t of 0v plus 0v equals t of 0v, and hence, because t is linear, the left-hand side becomes just the sum of t of 0 plus t of 0, and the right-hand side you just copy it. Okay? Well, but then t of 0v, because it's an element of w, it's the same as itself plus the 0 vector of w. And now you just cancel t of 0v. So whatever it was, you get t of 0v equals 0w, and so on. Now we know what it is for sure. Of course, this is structurally just like the proof we did for a scalar times 0 vector is equal to the 0 vector, and basically because multiplication by a scalar is also a linear transformation. That was in some sense a special case of that, of this thing we're doing here. Okay, I think I should mention the second proof, which is just you compute t of the number 0 times the vector 0v is 0 times whatever t of 0v is, but it's 0 times something. So that's the 0 vector of w, and of course the input is the 0 vector of v. Okay, so both are fine, but just remember t of 0 is 0, and this should not be something that causes any distress to anyone. We will use it all the time. Okay, so next there's a third result. I am on number 3, right? Yes, okay. Sometimes it's hard to keep them all straight in one's head. So a third comment is that t, again, linear, of the opposite of a vector is minus t of the vector, and here this is for all v in the domain. And reason, you just evaluate t of minus 1 times v, so that's minus 1 times t of v, and we've seen the rest before. Okay, or t of v plus minus v equals t of 0, which is 0, which we just saw. But by linearity, let's make it all capitals. This is t of v plus t of minus v, and now cancel t of v, i.e. add minus t of v to both sides. Okay, and I'm doing this for completeness. Honestly, you just have to do this once in your lives. You do not want to do this all the time, but just for you to get a feeling for how these issues work. Okay, so those are unsurprising and not very deep facts about linear transformations, but they are important and we use them all the time. Okay, so now let's talk about some subspaces associated to a linear transformation. So let's make this into the definition. Given t from v to w, a linear transformation. And when I say t is a linear transformation, in particular, v and w are vector spaces, okay? I mean, the word linear transformation includes the statement that the domain and the codomain are vector spaces. We define what right now are just two subspaces. So first thing, the kernel of t, which is ker t, to be by definition those v in the domain which t sends to the 0 vector, and I will put of w. And maybe I'll mention note, our book and many others call it the null space, and the book uses a fancy n of t. But let's say the majority of current mathematical practice is to call it the kernel, which is, you know, it sort of means the little seed in the inside of a fruit or a nut. In fact, the French word for kernel is noyau, but that's another story. Okay, so the way we've defined this, all we know is that the kernel of t is a subset. We do not know yet whether it's a subspace of, because it's those vectors which are sent to 0, and I'll give an example in a minute. Now the second thing is the image of t, and I'll write it as mt or maybe image t, depending on if I need all the letters. And this is, on some sense, an easier concept for people, but when you actually write out what it means, it's a bit harder to say. So this is all the possible values it can take. So sometimes this used to be called the range, but sometimes the range used to be the codomain. So let's just call it the image. So it is those w and w, and here there's a small subtlety, such that there exists a v where w is t of that vector. Okay, so informally, the image of t is the set of all the t of v's where v is in v. And this is actually correct mathematical writing, but for you at your early stages in Math 219, if you try to prove things about images from this statement, you might not realize the importance of the there exists, okay? So do things with the there exists, okay? So it's the set of all possible values of t, and then easily the image of t is a subset of w. Okay, these are sort of structurally the case because we are just limiting to certain elements of v for the kernel or certain elements of w for the image. Okay, and now there is a theorem kernel t is a subspace of v, and the image of t is a subspace of w. So they're not just any subsets, they're subspaces. And I'm sorry, the pen did not quite take that subspace of w. Good. Okay, so this is our situation. Let me give an example of this, and then I will talk a little bit about how it works. The general proof is actually quite straightforward, to be honest with you. However, I think it's helpful to see an actual example first. Okay. So, how about we use the same example like before? T, which goes from V, which is equal to R3, let's just write R3, to R2, with T of x1, x2, x3 equal to x1 plus x3, 2x1 plus x2 plus 9x3. So it's sort of T comes from the matrix 1, 0, 1, 2, 1, 9. Okay, but it doesn't really matter. Then kernel of T is the vectors in R3, that's the domain. So they have the form x1, x2, x3, such that T of V is the vector, the zero vector in R2. Notice I was careful to make it that the input, the domain is R3 and the codomain is R2. They are not the same vector space, so it's obvious when I write a vector which one I belong to. So this is the set of x1, x2, x3 in R3. Well, what is T of V? It is exactly the vector whose coefficients are in this matrix here. So if we want this vector to equal 0, 0, both coordinates have to be 0. So I must have x1 plus x3 equals 0, and simultaneously 2x1 plus x2 plus 9x3 equals 0. Okay, and so this is a solution of a system of equations with linear equations equal 0, so they're called homogeneous linear equations. And we saw before, as a warm-up, that this is an intersection of hyperplanes, and the first hyperplane being given by x1 plus x3 equals 0, and the second 2x1 plus x2 plus 9x3 equals 0. And if I can draw a picture, well, this is in R3, so it looks like that. So it's this. So the top plane here is the solutions to x1 plus x3 equals 0. The origin is here. You must always indicate the origin, I think. 2x1 plus x2 plus 9x3 equals 0 is the second. Plane, and the kernel of T is this line. And we know, as we've discussed before, that this is a subspace of R3. And if you want, note, we can find a single vector A with the kernel of T equals the span of A. Maybe I'll draw A in green here. Okay, and this is by Gaussian elimination, because if a vector x belongs to the kernel of T, then that's equivalent to saying that you satisfy the equations x1 plus x3 equals 0, 2x1 plus x2 plus 9x3 equals 0. I could think of x2 as being a bound variable, but then the x1 and x3 appear twice. So let's just eliminate an x1, our usual method. So this is the same as saying that x1 plus x3 equals 0, and then I remove 2x1 and remove 2x3, and I remove 2 times 0. I'm left with just x2 plus 7x3 equals 0. And now this is more obviously x1 and x2 are bound, and x3 is free. And saying that x1, x2, x3 equals minus x3, minus 7x3, and of course x3 is equal to x3, which is x3 times minus 1 minus 7, 1, with x3 arbitrary. So that's saying that the vector x is a multiple of the vector -1, -7, 1, and that's exactly a linear combination with that single vector. Okay, hence the kernel of T is a span of -1, -7, 1, and multiples of this vector are the only elements in the kernel. So that's maybe even more obvious that that's a line. Okay, let me now go on. I still haven't done the image of this, so let's do that quickly. Image T, so here, T of x1, x2, x3, remember was x1 plus x3. Notice how I write things in a way that's aligned, so it's easy to see what's happening. 2x1 plus x2 plus 9x3. And let's rewrite this as T of x1, x2, x3 equals x1 times the vector 1, 2 plus x2 times the vector 0, 1 plus x3 times the vector 1, 9. And notice these are the columns of the matrix A, where T is the transformation of A, and A looks like 1, 0, 1, 2, 1, 9. Okay, and this all makes perfect sense, and we will come back to why. Basically, but we're saying if a vector y, which is y1, y2, is in the image of T, is the same as saying that there exists an x1, x2, x3, such that the vector y is x1 times 1, 2, plus x2 times 0, 1, plus x3 times 1, 9. And that's the same as saying that y belongs to the span of those columns, 1, 2, 0, 1, and 1, 9. And this is a subspace of R3. Okay? So let's for instance, let's check. Is something like 2, 2 an element of the image of T? Okay, so the question is, does there exist x1, x2, x3? And when I say they exist, I mean at least one choice of x1, x2, x3, such that T of x1, x2, x3 equals 2, 2. So that means, does the following system have any solutions? At least one. Let's see it in that form. It's clearer. At least one solution. And the system is, well, what's T of x1, x2, x3? It's x1 plus x3 and 2x1 plus x2 plus 9x3. And we want this to equal 2 and 2, or maybe I should have made them 2 and 3. Well, never mind. And then the system is equivalent to what system? Well, again, you subtract 2 times the first from the second, and you get x2 plus 7x3 equals 2 minus 2 times 2, so that's minus 2. Okay, so one solution is x3 equals 0, the free variable, and then x1 equals 2 and x2 equals minus 2, i.e. 2, 2 is equal to T of the vector 2 minus 2, 0, right? I emphasize the x3 is the last coordinate because it's the x3. Note any other choice of x3, which is the free variable, gives another vector with t of v equals 2, 2, right? So if you play around with it. Okay, this particular example, it turns out, you can check this, that the image of t equals R2 here, but this is not always the case, okay? But here we are saying that every vector in R2 is actually in the image, okay? And that's not going to be always the case. For example, if t of x1, x2, x3 were, maybe we'll call it not t but t2, some new transformation was, how about x1 plus x2 and 2x1 plus 2x2, then you see the second coordinate is always twice the first one. And so you couldn't get anything you liked. You couldn't get 1, 1, because that wouldn't have the second coordinate equal to twice the first one. So here the image is what is called a proper subspace of R2, and I'll let you think about that. We'll talk about this in the actual lecture. I want to keep this a relatively brief video today. Great.